Hello, Uyuni community, and welcome to this mini series, 3 videos about some changes I've been working on at the content lifecycle management feature in Uyuni. Here we're talking about speedups, so performance optimizations. And here you can see some numbers about operations that used to be quite slow and becoming a little bit faster. What I will be talking in this video, in particular in this first video, is 3 things. First of all, a brief introduction on content lifecycle management. What is this feature? What is it about? Second, I'll try to point out a general strategy for optimization work, in particular on the Java code base, which is what CLM is actually implemented in, and perform the first steps of such analysis, such strategy, in particular by using the VisualVM tool. In later videos that I will publish again today, there will be 2 deep dives on what I find the most interesting problems in this area. One is specifics of Hibernate, and the other one is optimizations in form of query tuning in PostgreSQL. Okay, that said, we can probably start. What is content lifecycle management? Now, this is a feature you can find in Uyuni. Here we are looking actually at SUSE Manager Beta, which comes from the same development branch. So we are talking about something really, really close to Uyuni here. The feature is about management of software channels. And in particular, it allows you to create your own software channels in a very controlled way. Now, if you are a Uyuni user, you want to basically filter the content that gets on your clients. So for example, here we have a typical tree of channels, repos, that you might use for your clients. We have the base operating system channel, some extra channels, and in particular the channel with updates. And what you might want to do is not to distribute all updates to all clients, but stage them. So create your own versions of these channels to be able to select which patches go to which machine. For example, what you might want to do is to create different environments, for example, a test environment and a production environment, so that you are sure that before hitting production, all patches have gone through elaborate testing. And what you might want to do is to set up some filters. For example, hey, here I just want patches until 2019. Why? Because this is the last point in time where I had the full tests. So here I am pretty sure my production won't be impacted. So what you can do with content lifecycle management is to define a set of sources. In this case, we have the /12 sp3 channels. You can set some filters, and then you can build new channels, in this case end up here, which are the filtered versions of the channels that we've seen before. So as you can see here, it's basically the same tree with a different prefix and of course different contents. What you can also do once you have your first what we call environment, for example in this case test, is to promote content from one environment to the other. And then you can probably set up your clients to be attached to various environments so that you can control which patches go where and so on. So this is just a very, very, very brief, super high level overview. You can find a lot more detail about this feature in our official guide, of course. That goes in much more detail. What we care about here, we are talking about some specific changes that came in this pull request that are about speedups, is that content lifecycle management has 2 main basic operations, which are called build and promote. And we're interested in this because we want to split them up, and this would be a kind of a reference for the rest of this video and the other videos. So keep in mind, at the end of the day, CLM works on repos or channels, so it's pretty database intensive as a feature, and it contains it's made up of these two basic operations that are the targets for our optimization work. Okay, so how can a developer attack a problem like this in general? Of course, it's good to have a baseline, so to know what the current performance numbers are, and those are in this table already. I've just tried them out, build in promotion with different sets of channels that come from different operating systems in this case. And of course here we have quite a problem because, for example, building takes more than 24 hours. So we definitely want to speed it up. The second step, which I would always highly recommend, is to run the code through a profiler. A profiler is a tool that can show you what are the slowest operations in the piece of code that's being analyzed, so that you know where to concentrate your attention and where to act in order to make the code faster. So once you have the results from the profiler, you can look at them, find the hotspots, and then go really deep in each one of them and try to find solutions to make the code faster. So this is the general strategy. What we want to do now is to start the analysis and basically do the same things that I did when preparing this pull request to try to get back on the same path and redo all the reasonings and basically show you how this can be done in a different context. So first of all, as I said, we need a profiler, we need the profiler run, we need to take a look into that. How do I do that? We have in the Uyuni project wiki, we have pages that are dedicated to development, and they contain guides for different things that you can do around the code base. There are guides about how to set up a Java development environment, and there's many things that you can do to set up your ideal Java development environment, but the one that we are interested in today is profiling. So here you can see there is a full guide on how to set up VisualVM, how to attach it to an Uyuni instance or SUSE Manager instance is the same, and get data out of there. I will not go into all the details. If you want to do that, you just have to follow the guide. I will show you the result, which is here. And here I have VisualVM loaded with two profiles. One is for building, and the other one is for promotion, which are the two main operations I was talking about a while ago. So about building, here I've already selected out the one interesting thread, which is the only one that's really involved in building. And what we can see is that 100% of the time is spent into this run method, which is not surprising if you know Java. Now the question is, what is slow? So we have to dig into it, expand this node and figure out, okay, this is actually spending 100% of the time in this other run method, which does two things. Here, there is a call to pop event message and another one to run. Now, we're going a little bit deep in this rabbit hole. It goes deep pretty fast, so please bear with me for a few minutes while I dig in. Basically, we can disregard this one because this is just polling basically sleeping. And it's part of a subsystem which is not really involved in content lifecycle management. What we want to look into is this run method here. So we are really talking about this 38.6% of the time. This is actually the full time that it takes for building. So here is what we have to concentrate our attention to. And as you can see, all of the time is spent handling transaction, and all of the time is spent in this run method, and all of the time is again spent into small lambda and then the lambda, and now an execute method. And what the execute method does is to call these two methods, but one takes just 150 milliseconds, so we don't care. All of the time is spent here. And this is the crucial method in content lifecycle management, actually. It's called align environment target sync. What it does is to align environments, so promotes content from one environment to another. And here, what is interesting is that we have two methods this time. One is called align errata, and one is called refresh newest package cache. So one accounts for roughly 2/3 of the time that we're looking at, and another non-negligible part is spent in this method. I will dig into this first because it's easiest. If we go down to it, it calls another method which calls callable mode.execute. Now this is the method that executes a SQL query by using the mode query framework inside of Uyuni. Now in Uyuni, in the Java code path, there's different ways to issue SQL queries. One of them is called mode queries, and this is the main entry point. And if we go down further, what we see is that basically all of the time, now yeah, as I said, the rabbit hole goes down quite a bit, but basically all of the times, 11% that was actually in this method, refresh newest package cache, is spent in reading bytes from Postgres, which means Java is doing basically nothing. It's just waiting on Postgres to get the query back. So here, what we are seeing is one single Postgres query, which is particularly slow. And this is actually one of the directions to attack. And this will be the subject of the third video in this series. The second video in this series is all about this other method, which is the biggest actually. So we are talking about 27% out of 38% of the time. And here we have another problem, which is not related to SQL strictly. We can see it by going down a couple of more methods. So here we are in the clone errata method, which is kind of split up. We have 4 methods that make up this 27%. If we go down in the first, it's further split up in 2, and we get into that again. And here we have an update, which does some other operations, and here we have the culprit. So basically all of the time is 3% that is spent for this method, which is one of the 4 interesting ones for clone errata, is spent doing an internal Hibernate operation which is called flush. And this will be the subject of the second video. So keep that in mind. Flush is a problem for this method, which is method 104 inside of clone errata. Now let's give a look at method 204. What it does is call list, do list, and list auto flush if required, auto flush, flush everything to executions, flush entities, on flush entity. Basically it's flushing again. So here we see that against 3.9% of the time, so all of the time of the second method it's spent flushing. How about the third one? It's doing this method which finds the next prefix ending with flush. Again, same situation. What about the sibling? Let's rewind back. The last one, errata channel notifications, execute update, flush. So what we are saying, I've spent quite some time to figure it out, but basically all of the time that's spent into the most consuming method here is spent in Hibernate flushing. So what I can get out of this initial analysis is that we have substantially two problems, a slow SQL query and a problem with flushing. There is, truth be told, a third problem, and the third problem can be seen in the other operation, which is promotion. We have a similar profile trace in this case. Again, we can disregard pop-up and message. We're going to run that goes into a lambda, and most of the time is again spent in align environment target sync. And here again we have a similar situation. Refresh newest package cache is the one that calls the slow SQL query, and align errata does again something similar to what we had before. But there is a new one. So we actually have the same flushing problems that we have already seen here in this method, but we also have this other method, update search index. And what this is doing is invoking an XML RPC call from Tomcat to the RHN search daemon. Basically, this daemon, what it does is to provide Lucene full text indexing for searches in the UI. And this index has to be kept up to date when content changes. So what we have here is that we repeatedly call this method every time a new patch is inserted. Now we have a lot of patches, so a lot of calls to this method, and this slows down execution. This is actually the easiest of the three problems to solve, simply because it's sufficient to call this method to update the search index at the end of the computation, not once per patch. So I will not even go into details. It was just a matter of moving this call outside of some loops. We still have the two open problems, one with flushing and one with slow SQL query. So about those, I will just quit the video now, and you'll have to go to the next ones in order to learn more. Anyway, suffice to say that after these three bottlenecks were solved, we got these good results that you see in the pull request. So there was really nothing else. Now the main problem becomes to get familiar with the internals of those two situations and see how those can be fixed. So see you at the next video.